Last time on Engineering in the Digital Age, we examined how Model-Based Systems Engineering, MBSE, is used as the starting point in digital design. But what does digital transformation really look like? Our project, an autonomous vehicle, is a complex product that requires today's engineers to embrace digital workflows. This time, we look at one of the most important digital tools that's emerging in engineering and manufacturing: the digital twin. Imagine a high-fidelity and realistic digital mirror image version of your life. In that virtual world that looks exactly like the city you live in, a 3D avatar that looks exactly like you drives a car that's indistinguishable from yours. In a perfect simulation with very detailed 3D models, when the brakes on your virtual car start to wear out, it could inform you when to replace the real brakes on the real car at a real service station. That virtual car is a perfect digital twin. So is the city and the avatar. A digital twin is a complete virtual doppelganger of anybody, anything, or any process, and it's used to understand and analyze its physical counterpart. For practical engineering purposes, a digital twin doesn't have to be perfect to be useful. It just has to include the relevant details to provide the insight you need for the physical twin. In fact, the most useful digital twins represent the smallest set of data needed to complete or describe the product or system in development. That MBSE model we talked about in the first video would be a great starting point for a digital twin. The digital twin is a fundamental part of the engineering function when developing highly complex products and systems. In the case of our hypothetical autonomous car, it's impossible to physically drive the millions of miles needed to train a neural network how to drive. But we can create a digital twin of our autonomous vehicle, and it has no problem driving millions of virtual miles, without risking any harm to the car, people, or property. We can simulate any environmental condition and any driving scenario over and over, taking the very expensive and difficult development strategies used for decades in the aerospace industry and making them virtual, reliable, and affordable. The modern digital version of simulation as a development tool has far greater potential than the originally developed tools for the aviation industry. Engineers can now create a digital twin of a complete manufacturing facility down to the last fastener on the last conveyor belt to simulate and optimize processes before breaking ground in the real world. And as engineers go through the process of designing our vehicle and its various systems, we can continually leverage simulation to inform the direction of our design. Managing design change and tracking design revision history is an age-old problem of product development, and in this case, it's an essential link to the MBSE model. Integrated digital design platforms are key to maintaining the continuity of the digital thread, and ensuring all engineers, designers, analysts, and other stakeholders share the same single source of truth, even as it evolves and evolves quickly. Our digital twin does not die the minute our autonomous vehicle rolls off the assembly line. As useful as digital twins are for designing and manufacturing our product, their value goes much farther. In the automotive industry, prototypes and pilot vehicles are central development tools, but with a virtual vehicle and a matching physical car outfitted with numerous IoT sensors, our digital twin can continue to mirror its physical counterpart throughout its lifetime. And this can apply to every production vehicle on the road. A bidirectional link between the digital and physical twin serves several important functions. Using real-world input from the physical car, we can run simulations on the digital twin to predict its future behavior and schedule maintenance. We can also use the digital twin as a testbed for software updates to the physical twin, ensuring anything rolled out to the real car has been thoroughly vetted on virtual roads. And perhaps most importantly of all, by keeping the link alive between the physical and digital cars, we have an open window into where improvements are needed for our next generation of autonomous vehicles. Maybe our batteries are losing capacity too quickly. What would happen if we used a different chemistry or tweaked our battery management system? Since we have a digital twin already equipped to answer these and other questions, we can loop our digital thread back into the design phase of our next car. And just as importantly, we can minimize risk in both new product development and the implementation of running changes. In order for us to take full advantage of the digital twin, we need a way to keep connected with our autonomous vehicle in the real world. To do that, we need to go beyond the internet and enter the Internet of Things. We'll explore the IoT and how it fits into digital transformation next time on Engineering in the Digital Age.